Hanging in, hanging in with discrete mathematics. Good for you. Hey, Ronnie, good to see you. Hey, listen, tonight we are going to continue our discussion about uh, proof by cases. I've got a couple of interesting examples, or at least I hope you'll find them interesting. And one of the examples is going to allow us to look again at perfect squares. Perfect squares are kind of an interesting construct, and there are all kinds of fun things we can do with them. So tonight we're going to apply proof by cases to a statement about perfect squares. And I'm going to leave you with a do later that I promise you want to do later because it would make a great quiz or test question. So today is Wednesday, so October 16th. So we have a test coming up, not this coming Monday, but a week from Monday. Okay. And it's in the syllabus. Okay. So you'll be reporting to a room in York Road. If you're on campus, we'll use the same room we used before if you're a TU student. And of course, you'll be reporting to a room at Tune there at Hartford Community College if you're in the HCC program. Okay. I'll get you that room number next Monday. Um, it'll probably be the same room. Okay. All right, great. Hey, listen, I just want to double check. I got a concerning email from a student who said that I don't understand, why I'm getting the grades I'm getting on special homework, which indicated to me maybe not everybody in the room is aware that I grade your homework and I do write copious comments on your homework to try to point you in the right direction when you're losing a point here, a point there, or, whatever. Is everybody accessing the grade book in Blackboard? If there's anybody in this room who is not aware that there is a PDF that has been marked up and uploaded for you to review for every homework, and of course the test as well, if you have not found those for some reason, good gracious, please stick around after class. We'll stop the recording and we'll make sure that you find those because that's a big concern if somebody's saying, I have no idea why my homework grade looks like it does because I spent a lot of time writing comments on those for you. Okay. After we finish our proof by cases examples, we're going to run right into the next and last big topic for the chapter 4, which, as you have gathered, is the big chapter where we start writing proofs. And that's going to be indirect proofs. So far, we've been using the direct proof method, folks, right? We've been using good step 1 and 2, where we write the universal statement as an if-then. We take the if part, the hypothesis, as what we assume, and then we're always trying to prove the conclusion. That's our wish. That's the direct proof method. But as you'll see tonight, and I hope that I will motivate you with an example, not every statement lends itself to the direct proof method. Luckily, we have other options, and tonight we are going to start exploring methods of proof other than the direct proof method. Great. All right, so let's get started unless somebody's got a question. Does anybody have any questions? Good to see you, Kaja. All right, I got a chat. Let me open the chat. I'll be honest. I didn't expect the fall scenery. Okay, good. You noticed this screen turns around from spring to fall or crazy Van Gogh summer to fall, and yeah, I just turned it around tonight. So, oh, happy fall, everybody! Thanks for noticing. All right, here we go. I'm gonna take my glasses off because I need to. So the deal is our goals tonight, and these notes are posted, and obviously the notes are from an earlier class, but they'll be pretty darn close. Section 4.5 is we're gonna finish this. Okay, we're gonna finish with another two examples. We'll do two more. Two examples of proof by cases. So let's look at the gallery one more time. Hey, just raise of hands, did you write the case two of the statement that we wrote case one for on Monday? That statement was if n is an integer, then n squared plus 3n plus 5 is always odd. We wrote kind of the easy case where n was even. And the other case, of course, where was n equals nq plus 1. Q is an integer. In other words, n was odd in the second case. Did everybody write that up? No? Okay, Nick did. I'm getting a yes from Nick. If you need any help with that, if you wrote it up and you want me to look at it, just shoot me. It could even be a JPEG or a PDF. I'll be glad to read it over. I'm assuming everybody in the room can square NQ plus 1, factor out a 2, and show that it looked like 2 times an integer plus a 1 left over. I'm assuming that you were able to do that. Please do that if you did not attempt to do that. All these do laters are the real deal now. You can expect to see those kinds of questions on a test. All right, we'll get back to looking at the pinned. So we'll finish up section 4.5. By the way, section 4.6 is interesting. It talks about the floor and the ceiling functions. And as programmers, you may have actually drawn on libraries that have something that looks like a floor function or a ceiling function. Feel free to read section 4.6. And if you want to work through any of that, come to office hours or make an appointment. It is kind of interesting. We just don't have time in general to go through that during regular class time, but it's an interesting concept. So just accept my invitation if you would like to look through any of that material with me. So we're going to skip 4.6 in lecture, and we're going to dive into indirect proof methods. We're going to need them because some statements just do not lend themselves to our direct proof method. There are two indirect proof methods. One is proof by contrapositive, and that leans in on the fact that an if-then statement is logically equivalent to its contrapositive, right? If P then Q is logically equivalent to if not Q, then not P. Remember our very first example of an if-then statement? I think it was, if it is a rose, then it is a flower. That was our very first if-then statement. Well, the contrapositive of that is, if it's not a flower, then it's not a rose. Well, yeah, because if it's a rose, then it's a flower. And we verified using truth tables that if P then Q is logically equivalent to if not Q, then not P. And the upshot from that, the real takeaway is, hey, if we prove the contrapositive, we know it always has the same truth value as the original. They're logically equivalent. So we can prove the contrapositive, and in essence, we are proving the original because they always have the same truth value. So that's one of our main indirect proof methods. The other is proof by contradiction. We will not have time tonight to work proofs by contradiction, but we will start with that on Monday and finish with that on Monday. It will be covered on the test. And in fact, section 5.1, which we will work on Wednesday, is also going to be on the test. There will only be WebAssign on the section 5.1. It's cool stuff. It's cool set stuff and sequence stuff. I think you'll enjoy it. All right, so let's get started. And let's look again now at proof by cases. Okay, so here's our first example tonight. And I'm going to state it like this. The product of two consecutive integers is always even. Now let's just review, and there's a real reason I'm doing this particular problem. You have something quite similar on the next special homework. Think about the number line of integers. If this is, it looks like the real line, but let's just look at an integer situation. All right, so if we've got an integer n, the next integer is called a consecutive integer, and it would be n plus 1, right? That's the next one. What would be the one after that?
N plus 2.
Exactly. Thank you so much for your participation, Edwin. It's lovely. So on your homework, the problem is about the product of 3 consecutive integers. And I think I gave you the hint that it looks like n times n plus 1 times n plus 2. But to that end, let's work a slightly easier problem here, that the product of 2 consecutive integers is always even. Now, if we execute the good step 1 and 2 and write this as an if-then statement, which we're used to doing, we're still using direct proof method. Now, that doesn't mean to say that all proofs by cases have to have every case worked directly. Listen, I saw like a 99 case proof in knot theory worked over several hours at a math conference one time. And some of the cases were done by different proof methods, but we're only going to use direct proof in proof by cases. If n is an element of z, so I'm trying to kind of like, get myself grounded with an integer n, then when we want to talk about the product of 2 consecutive integers, so we're starting with n, how would we write the product of n and the next one? Well, it would certainly be n times n plus 1. So that's what we're thinking about, is always even. Okay. And so as usual, the good step 2 is to identify the hypothesis, which is the just simple, n is an integer. You'll find that the hypothesis of our problems that we work by cases is always very simple. It's an integer. We're looking at an integer, we're applying the quotient remainder theorem to the integer. And then this is the conclusion. We want to say something about this product. And in fact, we want to show it's always divisible by 2. Okay. So now in a proof by cases, we have 2 steps, and I just want to review those with you. Step 1 is just to identify the divisor that's in play, because our proofs by cases always hinge on having a divisor, because we always use the quotient remainder theorem. We always use the quotient remainder theorem to set up our cases. So we look at the conclusion. I think in the notes, the article "the" is missing, but look at the conclusion to discover the divisor D. So when we look and we say we're trying to show something is even, I hope everybody here realizes when we're talking about parity, the evenness or oddness of an integer, we're talking about dividing that integer by 2 and getting, a particular remainder, right? So parity, evenness or oddness indicates that D is 2, okay? If that's the result we want, that something is even or odd. And then the second step, when we are setting up cases, is to apply the QR theorem, the quotient remainder theorem, to the object in the hypothesis. It's always an integer. Using whatever D we found in step 1. And in fact, so in this case, we applied the QR theorem with D equals 2 to the integer n. In other words, we are going to eventually here, or actually at the beginning of the proof, say, hey, N is an integer, we can divide it by 2, and either we get that n equals 2q, this is a plus 0, although we don't write the remainder of 0, or n is equal to 2q plus 1. In both of these cases, q is in z. Okay. So let's start the proof. And I'll show you, again, we've done this once before, but we need to do it again, exactly how we write this up. So proof. Assume n is an integer. That's our hypothesis. Now, we wish to show that n times n plus 1 is even, right? That's what we want to show. We can do this. And, when you just look at n times n plus 1, if we didn't try to use proof by cases, just imagine, how are we going to show this is even? There aren't even any 2's in it. But by working proof by cases, we actually introduce the 2's, right? There's a 2 in the definition of even, there's a 2 in the definition of odd. That's how we actually get the factor of 2 that we need to prove our wish that this product, n times n plus 1, is even. So now I'll show you the wording to set it up. It's just like this. We just tell the reader, hey, by the QR theorem, you can just write QR theorem, with D equal 2, it is nice to tell your reader what the divisor is. We know, and then we just write this. We know that we can divide n by 2, and either n will equal 2q or n will equal 2q plus 1, where q is, in fact, an integer. Okay? So that sets us up for case 1, the case when n is even, or case 2, the case when n is odd. And that makes sense that the cases would be based on parity, since the desired result is about parity, evenness, or oddness. Any questions so far? Very good. Okay. So here we are. Keep this where we can see it for the moment. So case 1. Suppose that n looks like 2q. Where q, of course, is in z. We've got these two-part definitions of even and odd, and we're going to need both of these pieces. I know it seems like, n equals 2q is the only part that we need, but that's not quite true, because eventually we're going to have to, argue that some expression is an integer, and we'll have to know that the variable involved in that expression is an integer. So this is, actually quite important. So just to emphasize that the which, just to get it out of my own way, that the wish is going to be the same wish in every case. The point is this: we don't know what n is. All we know is that it is an integer, okay? So no matter what n is, we want to show that this product, n times n plus 1, is even. All right, so you don't have to do this, of course, but I'm just going to write it in the notes to emphasize to you as you review the notes that it's the same wish, whichever case you're working on. All right. And now we just dig in and we look at n times n plus 1, right? So here we go. Observe. N times n plus 1. Well, in this case, we've got this nice equation for n. It looks like 2q. So this is 2q times 2q plus 1. And we don't need to multiply this out. That's one of the things I want to emphasize with you this evening, is that you can make your life fairly easy with the algebra, especially when there's a product involved. Just find a factor of 2 in one of the factors, and there's a factor of 2 right here. This factor, 2q plus 1, does not have a factor of 2 that we can factor out of both terms, right? So we look to the other factor, and sure enough, there's the 2. So we just regroup that so that it's 2 times the quantity, q times 2q plus 1. And that, of course, this expression, q times 2q plus 1, is the m, that we'll use and argue that that's an integer. We're just a step away here from finishing the proof in case 1, that n times n plus 1 is even. We just have to argue that m is an integer. So here we go. Since q is in z, you see now I'm actually burning this piece of the proof money, that q is an integer. And z, I'm going to write it this way, but we'll write it the other way tonight as well. And z is closed under, let's see, what operations are being used to construct m here? I see some addition going on. Anything else?
Multiplication.
Yep. So closed under multiplication and addition, or addition and multiplication. We don't care, and doesn't care which goes first. We see m equals the quantity q times the quantity 2q plus 1 is an element of z. Don't forget to finish this thought. That's what we're shooting for. It is an integer. So, in fact, n times n plus 1 is equal to 2m, where m is in z, which makes it even. A definition of even. Two-part definition of even. We satisfied part 1 when we wrote n times n plus 1 equals 2 times, something. And then we satisfied part 2 when we argued that that something is actually an integer. Question? All right, case 2. The nice thing about, putting this information at the very top of the proof is that you don't really have to think too hard about it anymore. You can just look back and see, oh yeah, okay, I've got case 1, now I got to do case 2. So it just makes it actually easier for you to make sure that you have written everything that needs to be written to complete the proof by cases. Right? So suppose n equals 2q plus 1, where q is in z. And again, you don't have to rewrite the wish. I'm going to rewrite it here just to emphasize to you that the wish is the same no matter which case we're looking at. So we wish to show n times n plus 1 is even, or at this stage, if you want to say equals 2m, where m is in z, of course, that's a natural and good thing to do. I'm suppressing that here because even is such an easy definition, but generally that's a really good step to do. Let's take a look at n times n plus 1. So what does it look like now? Okay, so word to the wise, folks. We're substituting what's called a binomial, 2q plus 1. Okay, this is a binomial. It's got 2 parts. The parts are separated by a plus or a minus. Here it's a plus. N for what's called a monomial. N is a monomial. It's a single variable. We're substituting a binomial into a monomial. When we do that, we must use parentheses. They are not optional. When it's a factor, okay? Now, I'll put it in parentheses here just because you know what? If you always put it in parentheses, you'll never forget to do it when you really need to. You actually don't have to do it here because this is not an entire factor. It's a summand here of a factor. But anyhow, just make sure you put parentheses around this. I've noticed in Maryland high schools that high school students are graduating without realizing that this has to have parentheses around it. Just ask yourself, normally, would you put these two parentheses around 2q plus 1? If you don't usually do it, you need to start doing it. Okay. The point is this entire binomial has to get multiplied times the other factor, not just the plus 1 part. All right, so we'll just simplify the second factor and it becomes 2q plus 2. Now, again, I don't want to multiply this out. I just don't want to work that hard. I'm looking to pull out a factor of 2. 2q plus 1 does not have a factor of 2, but 2q plus 2 is equal to 2 times q plus 1, right? Let's put this little note on the side. So there is a 2 here that we can just yank out and leave the other factor, which is a q plus 1. That's the easiest thing to do. And now the product of these two factors is, going to be our integer m. You can just leave it like that and save yourself the trouble of all that work of multiplying that out. So let's just finish it now. We need to verify that this expression is an integer. So you can write it up, I'll write it up, and you can compare. All right, I'm rewarding it the other way in case you prefer that, that's fine. Now the little wrap-up sentence. Just verify n times n plus 1 is even. And that's the way it's done, folks. So on the test, obviously, I can't give you a proof that requires, a gazillion cases. 2 or 3 cases is reasonable. What I might do, what is possible, is I might ask you to prove a statement that would normally have maybe 5 cases, but I would ask you just to set it up and then actually only write maybe the first and the last case, for example. That would be fair game. But certainly you're going to see a proof by cases on the test. Questions? Let's do one more, but let's turn our attention back to the idea of a perfect square, because perfect squares are really kind of interesting. There's all kinds of cool things about perfect squares. By the way, let's go back to the gallery and see what's going on with folks. Did you enjoy the little short video about perfect cubes and perfect squares as far as the standard factored form? Was that helpful? I guess I shouldn't say, did you enjoy? I guess I should just ask if it was helpful. Okay. All right, so let's think about perfect squares. Let's imagine we're going to divide a perfect square by 3. Let's just think together about the remainders we might get when we divide a perfect square by 3. All right, so what's the first perfect square that comes to mind when you think perfect squares? Anybody?
0.
Yep, 0 is the smallest perfect square. When we divide 0 by 3, what is the remainder? Do y'all remember that?
0.
Yeah, it's 0. And just show it. Remember, we wrote 0 equals 3 times 0 plus 0 to prove it's in the 0 class. Can you see that? Okay, so now 1 is the next perfect square, right? 1 is 1 squared. What's the remainder that you get when you divide 1 by 3, people?
1.
Yep, 1 is 3 times 0 plus 1. All right, what's the next perfect square? After 0, 0 is 0 squared. 1 is 1 squared. What's the next perfect square?
4.
Sure. We divide 4 by 3. What is the remainder that we get?
1.
Somebody
1.
else, somebody besides Edwin. Although I really appreciate you're saying something. Come on, folks. Ah, we got 1. Ronnie, thank you. 1. Good. Because 4 is 3 times 1 plus 1. Thanks. All right. What's the next one? What's the next perfect square after 4, folks?
9.
9. Thanks, Ronnie. 9 is 3 squared. Let's divide 9 by 3. What's the remainder that we get? 0. All right, let's do a couple more. 16. That's 4 squared. What's the remainder when we divide 16 by 3?
1.
Trying to make a point here, folks. 1. Let's do one more. 25 is 5 squared. When we divide it by 3, what's the remainder?
1.
1. It's 3 times 8 plus 1. All right, you notice something here? What are the possible remainders when we divide any integer by 3, folks? Kaja, is it 1 or 0? It's not the only ones. When we're dividing by 2, the only possible remainders are 1 and 0. But when we're dividing by 3, there's another remainder we might get in general, not with perfect squares. So 2, right. So 0, 1, and 2 are the remainders that are legal when we're dividing by 3. Is everybody with me? If you can look at all the perfect squares you want, you're never going to get a remainder of 2 when you divide a perfect square by 3, which is kind of fascinating when you think about it in a mathy kind of way. Let's prove that. Okay, let's prove that. All right, so another fact about perfect squares. Example 2. Consider this claim. When a perfect square is divided by 3, the only possible remainders are 0 and 1. Or 1. I'll say 0 or 1 because we don't ever get this, get 2 different remainders for the same integer. That's the uniqueness part of the clause. Okay, so we're going to go ahead and apply our good step 1 and good step 2 to get this thing written in an if-then formula that's going to help us in an if-then form. Now I want to show you my first attempt to do this, and we're going to talk about why maybe it's not the best way to do it. My first attempt is, I want a variable, and I see this phrase perfect square, and it's talking about a perfect square. So I'm thinking, hey, why don't I write this? If x is a perfect square, then, and now we want to talk about x being divided by 3 and only getting a remainder of 0 or 1, the way we write that would be something like this. Then x is equal to 3k, or x is equal to 3k plus 1, where k is an integer. That's equivalent to saying when you divide x by 3, you either get a remainder of 0 or you get a remainder of 1, okay? So that is one way to write the claim as an if-then. And there's nothing wrong with it until you try to actually get the result that you want. And the problem with writing just x and saying, hey, x is a perfect square, is that we don't see the essence of what it means for x to be a perfect square written like this. The fact of the matter is, x is equal to n squared for some integer n if x is a perfect square. And we don't see that fact when we write the if-then in this form. So here's another attempt, and I think this attempt is going to get us a little closer to what's going to actually help. If n is just an integer, then n squared is equal to 3k, or n squared is equal to 3k plus 1, where k is an integer. You see, there we're actually going to see the power of what it means to have a perfect square. So it also simplifies our hypothesis now. N is just an integer, and everything is a little bit more clear. So we're going to attempt 2 is actually a better attempt at this. Is better, okay? Because it uses the fact that x is a perfect square. It doesn't just say it, but it actually uses it by calling x the n squared. We don't even see the x, but you can think of x as the n squared. So let's write a proof by cases. Before we do, we want to go ahead and execute step 1 and step 2 for setting up a proof by cases. Remember, step 1, we try to figure out what the divisor is, because for us, proof by cases will always be set up using the quotient remainder theorem. That's just the level of this class. Believe me, proofs by cases get set up all kinds of different ways. But for us, if we can manage this, we'll be doing really well. So let's look at the conclusion. What is the divisor, folks?
3.
Yeah, and that's good. You see, when we saw the claim written the way it originally was, we actually see divided by 3, okay? But you know what? The claim did not have to be written the way it was originally. The claim might be given to you in the form of attempt 2, written already as an if-then. So how do we recognize that the divisor is 3 if we are given the problem in the form of attempt 2? Well, just look at the conclusion. Something looks like 3 times k, or something looks like 3 times k plus 1. That is the form, BQ plus R, where B or D is the divisor, 3. And then Q is the K, and plus R. Well, here it's plus remainder of 0, and here it's plus remainder of 1. So you will see the divisor. In this case, D is definitely 3. And then step 2, we apply the QR theorem to the object in the hypothesis to set up the cases. So apply D equals 3. Oops. and the QR theorem to N. The object in the hypothesis. It's kind of interesting that these steps sort of in opposite order. I mean, when we read the statement, we read the hypothesis, then the conclusion. But when we're figuring out how to set it up, we look at the conclusion to find D, and then we apply it to the hypothesis. Here, N is either equal to 3Q, or N is equal to 3Q plus 1, or the other case, it's three cases, N is equal to 3Q plus 2, where of course Q is an integer. So these are the three cases that we have to deal with. Case 1, case 2, and case 3. Now, we're going to start this proof and we're going to write two of the cases. I'm going to leave the first case to you because that's the easy case. I want to show you the two harder cases. So please do write the first case, but let's set this thing up so that, it looks right even from the get-go. So here's our proof of our claim. It's a direct proof. Here's our attempt to that we're going to use. This formulation, assume N is an integer. Now this wish, matters. It's an interesting wish because it's a compound wish. The wish is an or statement. It is a disjunction. So we wish to show N squared equals 3K, or N squared equals 3K plus 1, where K is in Z. The reason that I want to make a note of this compound conclusion is this. Remember what it takes for an or statement to be true. We don't have to have both components true for an or statement to be true. All we need is one or the other component to be true. So in each case, our job is going to be to show that N squared looks like 3K or 3K plus 1. But in each case, it's only going to be one or the other. There's no way it could turn out to be both in a single case. Different cases will have possibly different reasons why this wish comes true. Like in some cases, it'll be because N squared looks like 3K. In other cases, this will be true because N squared looks like 3K plus 1. All right. So using the QR theorem, let's set up our cases. We have to do this inside the proof. That's one thing I noticed a little bit about scrap work. A couple of folks seem to think that if you did work in the scrap work, that it, counted as if it was in the actual argument that you were making. It doesn't. The scrap work is just to set us up and get us pointed in the right direction. And then everything has to be written up in the proof proper. Using the QR theorem with D equals 3, we know, and here we just write the cases, N equals 3Q, or N equals 3Q plus 1, or N equals 3Q plus 2. And you may not have to actually write out step 2, before you start. You may just need to make a note of, oh yeah, okay, that's what's going to happen here. And of course, Q is in Z. So case 1. I want you to do this, but let's just make sure that you have the right hypothesis to start case 1. Suppose, of course, that N equals 3 times Q. Just to make sure you know what you're trying to do in this case, I'm going to emphasize that this wish is the same wish in every single case. So let's just at least write the wish. We wish to show N squared equals 3K, or N squared equals 3K plus 1, or of course K is in Z. Okay, so you can do that one. Let's move on to case 2. The first case where N looks like a binomial, 3Q plus 1. me get out of my own way here. Oh, okay, Pippa. Pippa. There we go. All right. So case two. Case two is the n equals 3q plus 1. Gosh, I sure am glad I wrote my wish down because I've forgotten it already. All right, so suppose n equals 3q plus 1, where, of course, q is an integer. Again, you don't have to write the wish over and over and over again. I'm just doing it for the purposes of the notes to emphasize same wish every time. How we achieve it will be different in every case, or at least in some of the cases. We wish to show n squared equals 3k, or n squared equals 3k plus 1. K is, of course, an integer. Okay, so we're going to be looking at n squared. So let's check out what n squared looks like when n equals 3q plus 1. N squared equals 3q plus 1. That quantity is being squared. So we'll just, this is just 3q plus 1 times 3q plus 1, which is a grand total of 9q squared plus 6q plus 1. If you have a hard time multiplying two binomials together, come to office hours or make an appointment and I'll sort you out. Now, I'm trying to figure out, what am I trying to do? Oh yeah, I got to get this to look like either 3 times k or 3 times k plus 1. Which one of these two are we going to be able to achieve in this particular case?
3k plus 1.
Yeah, because this plus 1 hanging out, we'll never be able to pull a 3 out of that. So it looks like it's going to be 3 times, well, the k will be 3q squared plus 2q, of course, and then plus 1. And so now we're going to just argue that this expression, which is our k, is actually an integer, and we'll be done with case 2. So since q is in z, and sums and products, I guess that's all only operations we're using here. Sums and products of integers are integers. I totally recommend that you get some really good gel pens if you haven't already done it, or really good 0.7 HB lead. K equals 3q squared plus 2q is in Z. I'm going to write a little more than you have to write, but I want to make a point. So n squared is equal to 3k plus 1, where k is in Z. You need to write that, but I'm going to actually go ahead and point to the actual wish, which is an or statement, to make the point that what we just showed means the statement n squared equals 3k or n squared equals 3k plus 1, k in z, is true. We just established that that or statement is true by virtue of proving one of the two components. We proved this component, and that makes the or statement true. Questions? Oops. Last case is not case 2, it's case 3. All right, before we write case 3, I want to kind of head you off at the pass. The most common error, okay, for students is, even if you've written the wish down and you know what we wish to show, the most common mistake is that when we suppose n equals 3q plus 2, which is the third case, where q is in z, is to think that somehow the wish has changed and that we want to show that n squared looks like 3k plus 2. Not at all. That's kind of the point, is that the remainder that applies to the object n is not necessarily going to be the same as the remainder that applies to the expression that we're actually trying to make a conclusion about. We're trying to make a conclusion about n squared. It's never going to look like 3 times an integer plus 2. That's the point. So again, just to emphasize, we wish to show, and you don't have to write this in a good proof, I'm just doing it for the notes, that n squared equals 3k, or n squared equals 3k plus 1, where k, of course, is an integer. So here we go. Let's look at n squared and see what happens when n has a remainder of 2. N squared is equal to the quantity 3q plus 2 squared. When we square that, we get 9q squared plus 6q plus another 6q for a grand total of plus 12q plus 4. So when we look at this, plus 4 is not a legitimate remainder when we're dividing by 3. We're going to have to apply the QR theorem to 4 so we can break it down to look like 3 times something plus 1. In fact, 4 we can just write as 3 times 1 plus 1, or just 3 plus 1, you see. Because now we'll be able to factor a 3 out of the 3, and the plus 1 is the remainder. So this is 3 times the quantity 3q squared plus 4q plus 1. Whole thing now plus 1, and we have found our integer k. So in this case, n squared turns out looking like 3k plus 1, just like it did in case 2. And then we write it up. I know it gets tedious since q is in z. I'll write it the other way this time, and z is closed under, and you can abbreviate mult and addition like that. K equals 3q squared plus 4q plus 1 is in z. So n squared does equal 3k plus 1, where k is in z, in this case. So the desired conclusion, I'm just writing it a different way here, which was that n squared equals 3k, or n squared equals 3k plus 1, where k is in z, is true. Whew. So, you definitely want to practice these so that you can just pin them off without without having to stop and think too hard, because that's kind of the critical thing for test 2, is if you have to sit and think for a long time before you even start writing a proof, you're going to be in trouble. And because the proofs themselves require a goodly amount of time, just physically, right, to pin them off. So, questions? Let's just go back to the gallery here for a second. And I want to encourage you now to keep thinking about perfect squares, okay? But now think about dividing a perfect square by 5. What remainders could we get? What remainders can we get? 0 to 4. Okay. I'm so glad you said that. If we're looking at just a generic integer, n, and we're dividing by 5, you're exactly right, Ronnie. The legitimate legal remainders when we're dividing by 5 are 0, 1, 2, 3, and 4, right? There are 5 possible remainders. But now let's think about perfect squares. All right, so 0. 0 is the first perfect square. When we divide 0 by 5, what's the remainder?
0.
0. Good. 1, because 1 equals 1 squared. What is the remainder when we divide 1 by 5?
1.
1. Good. What's the next perfect square?
4.
What's the remainder when you divide it by
1.
5?
1. 4.
Yeah, 4, right? Let's check that one. 4 equals 5 times 0 plus 4. As long as the dividend is smaller than the divisor, the remainder is the dividend and the quotient is 0, right? When the divisor is bigger. All right, but let's go to the next one, 9. So far, 0 is 5 times 0 plus 0. 1 is 5 times 0 plus 1, because all these first 3 are actually smaller than the divisor 5. All right, so now 9. What's the remainder?
4.
Good. 16. Remainder.
1.
Everybody seeing what's going on here? 25. We're dividing by 5. What's the remainder?
0.
What's the next perfect square?
36.
Divided by 5. What's the remainder?
1.
1 more. 49. What's the remainder?
4.
Correct. Check it out. Look at the only remainders that we're getting when we divide a perfect square by 5. If it was just any old integer, we could get 0, 1, 2, 3, or 4. Every 5th integer would have one of those. But when it's a perfect square, you don't ever get a remainder of 2 or 3 when you divide it by 5, which I think is really fascinating. All right, so I'm going to give you a do later, and I encourage you to really do it later, because this would be a good test question where maybe I didn't ask you to write all 5 cases, but I might ask you to write, the first and last, or the 2 middle cases, or the first and third case, where, the remainders are in order in your cases. If n is in z, then n squared equals 5k, or n squared equals 5k plus 1, or n squared equals 5k plus 4, where k is, of course, an integer. So that's a proof in 5 cases. I guarantee you, if you do that and the special homework between those, you're going to have plenty of practice in order to do a good job on the test. All right, let's move on. Indirect proof methods. So just recall, the contrapositive is logically equivalent to the original if-then statement. So if the original looks like this, for all x in some domain D, P of x implies Q of x, then the contrapositive looks like this. For all x in D, if not Q of x, then not P of x. And these are logically equivalent. So if we prove one, we have in essence proven the other one. So here's a question. How would you prove this lemma? A lemma is a little statement that requires a proof, but then can be used in lots of other proofs later, kind of like a module that you write that you can just, call. For all n z, if n squared is even, then n is even. So let's just imagine that we were going to write a direct proof of this, and let's look at what goes wrong. What goes wrong is what happens when we start the proof and assume n is in z, and we assume n squared is even. That would be the hypothesis. And of course, we wish to show n is even by direct proof. So we apply the definition of even to n squared because that's our hypothesis. And we have that n squared equals 2 times k, where k is an integer. But let's look at what we're trying to show something about. We're trying to show something about n. Now, let me ask you this. What did you learn in high school or, recently, maybe in another class, that how do you get to n if what you have is an equation involving n squared? What's the general procedure to get our hands on n?
Square root.
Square root, right? So let's try that because we need to get an n. So we take the square root of both sides, and that lifts the radical. And we've got that n is equal to, well, of course, square root is actually the power of 1/2, so we can distribute it, and it's square root of 2 times square root of k. So n looks like square root of 2 times square root of k. That does not help us at all. This is not the definition of even, and there's no getting to the definition of even from this, you see? Because square root of 2 is not part of the definition of even. Not much we can do with that. So what I'm hoping to show you is, boy, direct proof method is not going to be helpful for this little simple statement. But proof by contrapositive, easy peasy. Let's write the contrapositive. Okay. Let me just show you the original lemma so you can see it. If n squared is even, then n is even. Now we know n is an integer, right? So here's the contrapositive. It's still universally quantified because it's still an if-then. But it's not Q, right? We want not Q. Well, that means n is not even, but n is an integer, folks. It's either even or odd. So if n is not even, that means n is odd. Then n squared is odd. And that's easy to prove. So when we write the proof, we do let our reader know that we're writing a proof by contraposition or by contrapositive. And just, assume n is odd. You don't even have to say it's an integer, because when we say it's odd, we're saying it's an integer. We wish to show n squared is odd. It's super easy, by definition of odd. n equals 2k plus 1. K is an integer. So n squared equals 2k plus 1 quantity squared, which is 4k squared plus 4k plus 1, which of course is 2 times the quantity 2k squared plus 2k, whole thing plus 1. This is our integer m, and then we finish writing the proof. It's included in the notes that are posted, but you can finish, argue that m is an integer. The reason I'm cutting a corner here is because I really want to get to the next proof by contrapositive, because the next one is going to help you more with your homework than this one. All right, so let's look at a different statement that also is not going to lend itself to direct proof. Somehow I spent too much time on the other stuff. I don't know how I did. I'm way off kilter from what I was this afternoon. Maybe I chatted too much about motivating me. Maybe we looked at too many perfect squares. Not sure. So consider this statement. For all A, B, and C in Z, if A squared does not divide BC, then A does not divide B, or B does not divide C. I want to do one of those. So if we tried to prove this directly, we're not going to get anywhere. Because the hypothesis would be that A squared does not divide BC. That gives us nothing. It gives us no equations. It only tells us that there are a whole slew of equations that don't hold for A squared and BC. See what I mean? It doesn't, there's just nothing, we don't get anything from not divides. So we write the contrapositive. And there are a few extra notes that are posted, just, like the question, what would we be assuming if we try to direct proof? And I write down, it gives us no equations. So contraposition, if we write the contraposition, suddenly things change. It's still for all A, B, and C in Z, because of course the contrapositive is still universally quantified. But now we negate Q, and that will become our hypothesis, and not P will become our conclusion. So everything you learned about negating and or statements now matters. De Morgan's laws and learning to negate statements matters, because we have to be able to negate A does not divide B, or B does not divide C. Of course, that becomes if A does divide B and B does divide C, then not P becomes A squared does divide BC. And now we've got something that we can do something with. Questions before we move to the proof, which will be good review about definition of divide. You're holding your head there, Kendall. Are you okay? All right, everybody with me? See, this is just a divides proof. We've done these. So proof by contrapositive or by contraposition. Assume A, B, and C are in Z. Assume A divides B and B divides C. What do we wish to show? We wish to show A squared does divide BC. Okay? We can do this by definition of divides. Here we go. A divides B means B is equal to A times K, where K is an integer. B divides C means C equals, I'll say B times H, where H is an integer. I am going to go ahead and expound on my wish because this is divides. It always confuses me. I want to show A squared divides BC. So that means we wish to show that BC equals A squared M, where M is an integer. Using the definition of divides over and over and over again here. Here we go. We're going to look at BC. And we're going to use a double substitution. All right, BC is equal to, okay, B is A times K, C is B times H. So I've used these two pieces of proof money. But I'm looking at what I have here. I've got A to the 1, K, B to the 1, H. But when I look at my wish, I see I need 2 copies of A. I need an A squared. I don't have that. So how are we going to get an A squared? I've got 1A, but look at the B. The B, I can substitute again. It's AK times H. You put the AK in for B again. And now suddenly we've got A squared times the quantity K squared H. And K squared H is going to be the integer M. So since K and H are in Z, the only operation being used to build M is multiplication. We could say M equals K squared H is in Z because Z is closed under multiplication. So BC equals A squared M, where M is in Z, which means A squared divides BC as desired, or by the definition of divides. I mean, there comes a point where you get really tired of saying the same thing over and over, and then we get a little creative. So a favorite, just FYI, you've got one of these does not divides problems on the next homework, okay? So you should be able to work it. It's obvious what the proof method is, based on our discussion here. And I just want to encourage you to be sure and make it to class on Monday, because we have got a really nice, here, let me move my camera. A really nice thing that we get to do. You are ready to prove that the square root of 2 is irrational. And if you think about what you knew when you came into this class in August, and think about the fact maybe you'd never proven much of anything, but you've learned the tools now. So Monday, we're going to prove that the square root of 2 is irrational. And I think it's amazing, honestly, that in 8 weeks, 9 weeks, whatever it is, that you can get to the point where you're going to understand that proof, that the square root of 2 is irrational. And we're also going to learn that if you take a rational number and add it to an irrational number, that sum is always irrational. And you're going to understand those proofs. Those proofs are not proof by contrapositive, but it is the other indirect proof method that we'll be looking at on Monday, and that's proof by contradiction. So it's a little more involved. We'll talk about the logic behind proof by contradiction, and then we will prove a couple of things by contradiction. There will be a mini homework that'll be due on, I can probably give you till Thursday, just one or two problems. I do want you to practice a proof by contradiction before the exam. So there'll be a little mini homework with just one or two problems next week. And I'll grade it, of course, and you'll get your uploaded, graded mini homework. And then section 5.1, we will cover on Wednesday. The only homework on section 5.1 will be from WebAssign. So we'll cover what we can from 5.1 that can be covered with WebAssign, and that will all be on the test the following Monday. But you'll get plenty of feedback. So thanks for playing. Thanks for being here. I hope you have a really great rest of your week. I'm running a little overtime, so I should shut up now. I'll stick around. Yeah, bye, Eric. I'll stick around. And if you want to visit about anything, I'll be here for a few more minutes.